Another example problem. I don't know if you'll actually need this, but maybe it'd be helpful to somebody. I don't know. We'll see. Okay, so I think this is another 3-force member problem. And we have this T-shaped bracket that supports a 300 Newton load. This is 60 degrees right here. And we want to determine the reactions at A and C. You can see that this is a roller joint, so it's only going to have a reaction in the vertical direction. This is a pin joint, it would be vertical and horizontal. So we start off with our FBD, declare X and Y, and make a nice drawing of everything. And we'll put the reactions right here. This is going to be our RC, RCY, RCX. We're going to have a reaction right here. This is going to be our RA, maybe RAY, but there's no RAX, so we'll just leave it in there. This is drawn like, that looks like more like 30 degrees, so I think maybe we could help ourselves out by trying to make it look a little bit more accurate. That right there is 60 degrees, right? And this is 300 newtons. And we get some dimensions on there. Let's say we did it in millimeters. Okay. So there's 300 millimeters right there and there. This distance, probably I'm going a long leader on 150, and in this distance we get 250. Like a cheat, just go right there. All right. So the sum of the moments. Let's take it about C first. It's equal to 0. Take a look at this, and RA is going to go counterclockwise about C with a moment arm of 150. So RA times 0.15, and okay, so this guy, he's going to have a downwards component, and that downwards component would be clockwise, so 300, and that's going to be, the downwards component is cosine of that, cosine of 60, and that's going to have that moment arm of 0.250, right? And I have to go down to the next line because I wrote it, started out over here. And now we have the horizontal component of 300, and that too is going to go counterclockwise, so minus 300, but now it's going to be the sine of 60, which is opposite from the angle right there, and its moment arm is going to be 300. And if I do that, let's see, double check. Yes, I get 769.6 newtons, and that's downwards. So that's one of my answers right here. Now I need it at C, so we take the sum of the forces in the x direction equals 0. And that's going to be RCX. I have it pointing to the right. We could observe it's going to be to the left, but we have it drawn that way. It's going to be plus our 300 times our sine of 60. RCX is negative 259. I don't want to put an arrow in there yet because I have a negative. But we know it's that way right there. Okay. And then sum of the forces in the y direction, upwards is positive. Take our RCY, subtract out our RA, which we just got 769.6, and also now the minus 300 times the cosine of 60. And then, so RCY ends up being 919.6 newtons. And so if we have the RC is the square root, we might be asked that, right? Of 259.8 squared plus 919.6 squared. We get 955.6 newtons. And the reaction angle onto the thing would be the inverse tangent of the rise over the run. So the 919.6 divided by a 259.8, and I don't advise you to use the negatives inside there. It's just think your way through it instead. You get 74.22 degrees, right? So the reaction at C is 955.6 newtons, and we notice that this one is going to the left and this one's going up, so we're going to have, that's going to be the direction of the angle, 74.22. And now let's take a look, just like we did on the other one. Let's graph this one. Let's take a look. Ooh, let's focus. Focus a little bit more. Document camera a little bit higher. That's nice. That's a good document camera. I like that document camera. Okay, so I think I'm okay. Let's see. Take and draw this thing out. This little T. Make it kind of proportional. Doesn't have to be right. Doesn't have to be perfect. It's my little Bob Ross voice. There we go. And this one was down. And this one was at 60 degrees. So that's going to be something like that right there, right? Something. Right? Because that right there was 60 degrees. So if we extend these lines out, we can expect this guy down here to intersect at that concurrent point right up here, right? So what I did, and I did it, here's mine. I actually drew it a little bit smaller, and I was able to get all the way over there. And then okay, I didn't actually need to do that. Okay, I think I'm good. So I'll do this in a different way here. Let's see, this dimension on here was 250 to get to right there. And then, I don't know if I need that. No, I do. Okay, yeah. So what I really want to do is I really want to eventually get to this right here and this right there, right? And if I can get those, I can figure out that angle, right? If I have that dimension, which I already possess as 150, and I have this dimension right here, which is 300, up to there, right? To the center of that. So what I really need to do is find out what this dimension is and add it to my 300, right? And I know that this is 30 degrees right here, right? Because this was 60, and this, so this must have been 30, so that must be 30. So, and by the way, this dimension, 150, right? What we got from that right there. So, let's see, what I want to do, I'll take a little cheater look over here, is I can say, I decided to call this E, call that D, because I think everybody else is taken, right? Because that was C, and this was A, and this was B. Yeah, okay, so that's E, and that's D. So, let's see, I take AD, okay, yep, AD is just going to be equal to my 150 plus 250, which is 400. 400 times the tangent, right, because this is the run, so I can multiply by tangent and I get the rise. Tangent of 30. And I end up with 230.9 millimeters. And then I can take my DE, it's this distance right here, is going to be my AE plus my AD, so that's 300 plus my 230.9, I can do that, 530.9 millimeters. And then I already know that my CE was equal to 150. So I'll call this one beta. I like beta. And take the inverse tangent of my rise over run, which is going to be my DE, over my CE. My inverse tangent of 530 over 150, and I get a 74.22 degrees, which, boom, matches this right here. So I have demonstrated. Ta-da! Woohoo! Yay! Great hair day. So we have an 11-minute video. Not bad. I like 10.